Of course, there is something in between. Okay, good. The signal I have is essentially the number, and fundamentally the noise is basically our base, which is in essence the signal. It is considered the opposite of relative noise because relative noise is sigma over n, which means the square root of n over n2 with n on it, right? So you will find that the SNR here at 1000 is 31, while here at 100 it is 10, resulting in an increase in the signal to noise ratio. So, an increase in the number of photons causes a decrease in relative noise, right? An increasing number of photons reduces relative noise and increases the signal to noise ratio, right, doctors? I think this part has confused a lot of people, and I hope I can help you understand, God willing. Thank God, there is a relationship between noise and, as we were discussing, milliampere. There is a rough comparison between milliampere seconds and noise. When you increase milliampere seconds, you increase the dose for the skin, and there is no disagreement about this. Now, the relationship between noise and the square root indicates that when milliampere seconds increase, it means it is inversely proportional, which means that it leads to a significant effect. If you reduce milliampere, this is the relationship. However, increasing the light by about 41%, as I said, reducing milliampere by 50%, you will find that the amount of light decreased by 41%. These values in front of us relate to the increasing milliampere seconds and the patient dose, which is the SDI, the standard dose index. We can talk about this part in the design, but I don't want to get into it now. I want to continue with the topic of design, especially the relationship between sound and milliampere. The more we discuss milliampere, the more it will reduce the noise for me. For example, in the two images present, which are image A and image B, you will find that there is noise present along with a reduction in milliampere. Now, regarding the house field unit or the standard deviation. When you take the region of interest on the image city, it shows you the mean, maximum, minimum, and standard deviation. Normally, when you find the value of the standard deviation here, this value, if you were to take the mean value and calculate its square root, would not be the value that comes out. Because when we said that the number of photons should be the square root of the mean in the case of a low number of photons. If I were to talk about quantum noise, you would find that your standard deviation should be large when the number of photons is low, meaning when we were discussing this. Here in this example, here the number of photons is low, and here the number of photons is high. The standard deviation here is 10, and here it is 31.6. Is this what happens when you take a region of interest and find that a patient received a low dose? When you take the region of interest, you find that the standard deviation is low with a low dose. No, you find that the standard deviation that comes out on the image is large, not small. You need to pay attention to this point, because when you come to measure using the region of interest, you should know that the value of the standard deviation is not calculated in the same way. This method is the statistical method, or the one that expresses the Gaussian distribution that exists. However, the method he is using is related to his software, which examines every pixel present and starts calculating its variation. He does not take the values as absolute values and work on them with a square root. Rather, he looks at how many pixels are present and begins to create the real distribution of the values of the number, or the real distribution of the values inside the pixel. So, it is not necessary for the distribution of the pixel and its values to take the Gaussian shape. This distribution can actually vary. This is a point of statistics I am mentioning to you so that you are aware, because when you come to measure the ROI in an image that has noise or in an image that has low MA, you should know that the number of photons here is low. However, the issue is not only related to the number of photons, it is also related to the number of pixels present. The variation in the values between the pixels within your region of interest is important. Just remember this point, but it doesn't relate to anything else. I will change something from what I was talking about earlier, just so you know. When you take the region of interest, you will find, for example, that the standard deviation in the first image is 9 house field units. Here, you will find 21 house field units, and here, 36 house field units. The equation for relative noise is correct. As the standard deviation increases, your noise will also be high as a standard deviation value. Just be careful with this point, so you don't confuse it with the statistics part and ask how. Here, the region of interest was taken and it was awakened in low noise, resulting in a standard deviation of 96.5. Meanwhile, it was awakened in 30 emissus with the same quality, so the value of the standard deviation decreased. Therefore, your rarity of noise decreased. Don't fixate on the error that makes you do this. For example, he is calculating in a certain way. I'm telling you this because you can make a comparison. You can also tell him the standard deviation here and so on. But if you take the mean value of the rows you have and calculate its square root, you won't find it equal to the standard deviation that comes out. Do you understand what I'm saying? So now you are taking the mean, right? This mean comes out to a certain value, let's say 100, and it gives you a standard deviation. You will find that this standard deviation, the value that appears on your screen, does not equal the square root of the mean. How is it calculated? Well, it's a specific method, and I'm telling you this because you will find that this is done with an increase in the noise present. This is what we discussed. There is no difference. There is no difference, but you might try to say that the value I got is not what you will find. It won't equal that. Noise and its effect on the objects present within the scanned organ. For example, if I have different objects like this, some have high contrast and others have low contrast, meaning their contrast or physical density is low. Therefore, the contrast between them and the background is low here and high there. In the case of low noise, the effect on me won't be very significant. However, when the noise increases from medium to high, you will find that those most affected, or where the impact will be high, are the low physical density objects. Consequently, this reduces the contrast of low density objects for me, which means it decreases the contrast of low density objects. So, an increase in noise makes the low density objects you have less visible, for example, if you come to scan something. For example, when you come to take a picture, let's say you are imaging a kidney with a stone in a scanned organ. This is considered physics. You will find that with an increase in noise, the stone will still be visible and you can see its contrast. For example, if there is a lesion in the liver, with an increase in noise, the contrast in physics between it and the background starts to decrease. This is because if it has low physical density, The contrast between it and the background is low, so noise affects it and causes distortion or reduces its contrast. I'm not sure if anyone wants to join in. Is there any to say? Nishi, here, for example, is an image of the phantom used to test the issue of noise present in these images, which is a critical factor in image analysis. You can see that there are objects here, and when such unwanted noise increases within this visual representation, the physical contrast decreases significantly. As you can clearly see, the contrast isn't very noticeable at all, while this object remains visibly present here. The increase in this disruptive noise had quite a significant effect indeed, but even more so was its greater impact upon low contrast levels, which refers specifically to low physical density contrasts between said object and its surrounding background environment. Additionally speaking, size matters greatly. A small-sized object becomes much more affected by intrusive noises than does any larger one would be under similar circumstances. So then I have two things, both being firstly, a small-sized item, and secondly, another low-density type of thing, both affected adversely due entirely unto their presence amidst ever-increasingly noisy conditions, thereby reducing overall contrasts seen within smaller items inside imagery, whilst decreasing those found among lower density ones therein. Here, it expresses the concept of relative contrast, or contrast with object size, noting that an increase in noise will obscure the low contrast objects present, regardless of their size. It will create invisibility in the low contrast areas compared to the high contrast or high density objects that can be seen. The noise will have a delayed effect on it or will not be significant, unlike the low density object present. When we return to the topic of X-ray imaging and discuss the ideal imaging condition, we mean what conditions should be in place for imaging patients. The ideal imaging setup should include the organ that you are imaging. What is your situation? What should be present? Ideally, for X-ray imaging, the organ you are imaging should be parallel to the image receptor. This is my image receptor, and this is the body part, or the thing I am imaging, and this is the X-ray tube. So, the part I am imaging should be aligned with my image receptor, and at the same time, aligned with the X-ray tube in this way. Additionally, the central ray, or the incident X-ray from the X-ray tube, should be perpendicular to the part I am imaging. This is considered the ideal imaging condition for the imaging process, as well as the distance between the image receptor and the X-ray tube. There are terms used like SID or FID, where S stands for source, I for image receptor, and D for distance. Sometimes FID refers to focus image receptor distance or the focal point, which pertains to the focal point of the X-ray tube. All these terms essentially refer to the same concept, so there is no difference. Now, if we talk about FD, which is the object to film distance, the object to film distance and the source to image distance should be the same. This means the distance between the part I am imaging and the film is exactly this, and the distance from the X-ray tube to the film represents the ideal imaging condition. Any change in this ideal imaging condition affects the outcome. Any change in the imaging conditions can affect unsharpens or cause blurring. Unsharpens means that you are reducing the resolution, which in turn increases the blurring effect, making it difficult to define the margins or detect the edges of the object being imaged. This can occur, for example, if you apply magnification to the image in some way, leading to an increase in the blurring effect or unsharpens and a decrease in resolution. Additionally, if there is movement, such as the object shifting, this will also increase unsharpens or blurring and decrease resolution. For instance, if you move your object away from the image receptor, this will increase the penumbra or blurring while simultaneously reducing resolution, as we will discuss further shortly. You will move away from this everything that will happen to you or the effect. If I come here in the image that I see, I increase the distance between what I am imaging and the film. Is that clear? So what will happen? What will happen in this case is that if you increase the distance between the object and your image receptor, for example, I have two objects, as you can see, and I made the distance between them and my object large, which means my SID is large. Then I took a picture of another object and brought my X-ray closer to my object. What will happen? What will happen is something called magnification. This magnification is the enlargement of the size of the object that appears. This magnification, as you may know, has something called the magnification factor. The magnification factor is what we call zoom. This zoom can have some post-processing effects, but the magnification related to the imaging acquisition itself is the magnification factor. What is it about? It is about the image size in relation to the object size. You will always find that the size of the image or the size of the object you are imaging is larger than the actual size of the object itself. So you will always find that the magnification factor will naturally be greater than 1 because magnification occurs. When you bring the object very close to the image receptor, you reduce the magnification. By reducing this magnification, you maintain the resolution. When you perform this magnification, it increases the unsharpness or decreases the resolution and increases the blurring effect. So when does this happen? It is related to the distance between the X-ray tube and your object. If the distance, which is the SID, between your source and your image receptor is large, then the magnification that occurs will be minimal. If this distance is small, then the magnification will be greater. The magnification that will occur will be significant. So, this is the magnification. I mentioned here the magnification factor, but it is the magnification itself. If I move my object closer to the X-ray source, I am now fixing the X-ray source. I did not move the X-ray source. Last time, I was moving it closer to or further from the image receptor. This time, I am fixing the X-ray source, and it is my object that is moving. The same idea will result in magnification. When the distance between the object and the image receptor increases, your magnification increases. Conversely, if you reduce the distance between the object and the image receptor, your magnification decreases. If magnification increases, it increases the blurriness and reduces the resolution. So, I have two factors affecting the magnification: the distance from my object and the distance from the object to the field. We have increased the distance. When the object and the X-ray fill or the image receptor are increased, the magnification increases and the resolution decreases, or the unsharpness increases. If I reduce the distance between my object and the image receptor, the magnification decreases and my unsharpness decreases as well. Now, regarding the SID, which is the distance from the X-ray source to the object, if you increase the distance, you reduce the magnification. If you decrease the distance, you increase the magnification and the sharpness. Is that clear? All right. The topic of magnification is called distortion. It is not just about doing or for the object you are imaging. For example, if you take images of the same organ, one may experience one outcome, another may experience a different outcome, and so on. This is a result of the magnification that occurs because you are not adhering to the proper techniques. Now let's return to the equation. What you're saying is that the magnification of the image size compared to the object size will always show that your image size is larger than the object size. It must be magnified, even if it's just 1 millimeter larger than the existing object. So, that's the point. Why does this unsharpness occur? As we were discussing, here the object and the focal distance are close, but as the distance increases, you start to notice the area of unsharpness. As I mentioned, why does this area of unsharpness happen? Because simply the edge you have has X-ray photons, for example. Coming from your focal spot, these are directed at the object area. This same area is exposed to X-ray photons coming with a different intensity from these focal spots. So when you get here, or the part that is on, it's as if you have two coming from the same place, from the same location. Therefore, when it translates this onto the film, it creates the blurring that exists as if the signal is not coming from the same place. It translates this point onto the gray value. However, this point has two values that it takes when it processes them on the film itself, creating a blurring effect or unsharpness effect. Now, how does this increase? As we said, from the distance between the object and the focal spot. If this distance increases, then you have less blurring. The closer the object is to the image receptor, the less blurring there will be. The further away from the image receptor, the more blurring you will have. Okay, there is essentially something called the magnification factor. This magnification factor is basically the ratio between two things: the source to image distance, SID, and the source to object distance, OID. So, if you want to know what your magnification factor is, you need to know the distance between the X-ray source and the image receptor, as well as the distance from the source to the surface of your object. For example, if I give you an example here, This is, for example, an AP projection for a knee case with a source to image distance, SID, of 40 inches and an object image distance, OID, of 3 inches. In this case, the source to object distance for the session will equal the difference between SID and OID, which is 40 inches minus 3 inches. So, in this case, the source to object distance will equal the difference between SID and OID. If you want to bring this, you will subtract from the object to image distance. This difference will give you a nice SOD. We had obtained the SOD and the SID with the magnification factor, which is the SID divided by the SOD. That is 40 over 37, and you will always find 1.08. 1.8, the magnification factor. If you want to find the real size of the object, how will you get the real size of the object? You will use the equation we were discussing, which is that the magnification factor equals the image size divided by the object size. Once you have the magnification factor from the equation, you can obtain the image size from your device. If you want to know what the object size is, you will divide the image size by the magnification factor to give you the real object size, because it will appear as if you are dividing it by the amount of magnification that occurred. So you want to obtain the real object size. Is that clear? What happened is that you want to get your real thing. When we talk about unsharpness or the blurring effect, there are reasons related to magnification. And we said that it is fundamental.